Hello students, welcome to EPG Pathshala. I am Professor P.N. Kotru from Jammu. Today we are going to discuss about a module entitled Color Centers and Polymorphism under paper Crystallography and Crystal Growth. So students, let us see what we are going to learn in this module. We are going to learn concept of color centers in crystals, different ways of coloring of crystals by addition, different types of color centers, color center models, and phenomenon of polymorphism. In the previous section, we have learned about certain type of point defects and that the presence of either Schottky defect or anti-Schottky defects bring about a change in the density of the crystalline solid. Very often, this change is small because the actual number of such defects present is always very small in comparison with the total number of atoms or ions present in the crystal. However, we come across situations which are quite interesting. A crystal of sodium chloride is ordinarily transparent and uncolored, but it is well known that if this crystal is heated in the presence of sodium vapor, the crystal turns yellow. What has brought about this change in sodium chloride crystal? The explanation is that by heating sodium chloride in sodium vapor produces defects by creating vacancies at the sites of chlorine, that is Cl negative ions. Since a sodium atom is introduced into the structure, which means that a sodium ion and an electron are produced. The ion gets adjusted at any of the proper sites for a sodium ion in the lattice, whereas the electron is relatively free, which wanders around in the lattice. The removal of a negative ion from a particular site means that in the region around that vacant lattice site, there is an excess of positive charge around that site. There is a possibility for the wandering free electron to be attracted to this net positive charge and get trapped in the vacancy created by the chlorine ion which left the crystal. In this way, we have an electron which is moving in a region of positive charge. The situation may be compared with an electron in a hydrogen atom which moves in the field of a positive charge, that is the proton, and could be in very approximate way described as being similar to the Bohr theory of hydrogen atom. According to this theory, the electron will only be allowed to move in certain orbits in which does not radiate energy, while other orbits are for forbidden orbits. This situation is shown in figure 19.1. The situation is shown in figure 19.1. There is a probability for the electron to jump from one orbit to another, and in this process it may either absorb or emit a quantum or photon of energy. The frequency nu of the radiation which is emitted or absorbed is given by the relation E1 minus E2 equal to h nu, where E1 and E2 are the energies of the electrons in the two orbits. It so happens that for the alkali halide crystals, the frequency of the radiation is involved in the visible part of the spectrum. Sodium chloride crystals, which are heated in excess of sodium vapor, become colored. The vacancy created at the site of chlorine ion, along with the trapped electron, is called a color center. Ordinarily, a crystal is transparent to the visible range of spectrum. So, a sodium chloride crystal should not absorb visible light and is expected to be perfectly transparent. Crystals which are colored contain defects known as color centers. Defects in the lattice which absorb light are called color centers. Coloring of crystals can be achieved by different ways, as is described. Number one, by addition of suitable impurities like transition element ions with excited energy levels. Number two, by adding stoichiometric excess of cations by heating the crystal in the alkali metal vapor, followed by quick cooling. The color of the crystal would depend on its nature. For example, KCl, that's potassium chloride, when heated in excess of potassium, vapor becomes blue. Sodium chloride, that's NaCl, when heated in excess of sodium vapor, becomes yellow. And lithium fluoride, that's LiF, when heated in excess of lithium vapor, turns pink. Number three, crystals can also be made colored by exposing them to high energy radiation like X-rays, gamma rays, or irradiating them with energetic neutrons or electrons. There are several different kinds of color centers, and the simplest one is called as F center. F center is a defect in crystals where an electron is trapped at a negative ion vacancy. Its name has come from the German word Farbe, which means color, and F centers are also named as Farbizentron. These centers are generally generated by heating a crystal in an excess of alkali vapor or by irradiating the crystal by X-rays. Sodium chloride having F centers show main absorption band at about 4650 angstroms and is shown as F band. Figure 19.2 shows optical absorption plotted against wavelength of some alkali halide crystals. The F bands associated with the F centers of some alkali halides are shown in figure 19.2. Figure 19.2 shows optical absorption versus wavelength in case of some alkali halide crystals. When point defects in a crystal trap electrons, color centers are formed with the resultant electronic energy levels spaced at optical frequencies. The trapped electron has a ground state energy which is determined by the surroundings of the vacancy. These energy levels lie in the forbidden energy gap, and relatively widely spaced levels change to an almost continuous set of levels which fall just below the bottom of the conduction band. Should the crystal be exposed to white light, the energy excites the trapped electron to a higher energy level. It is absorbed in the process, and a characteristic absorption peak corresponding to near visible region appears in the absorption spectrum of the crystal with F centers. The peak does not change when an excess of another metal is introduced in the crystal if the foreign atoms get substituted for the metal atoms of the host crystal. Therefore, making an assumption that the absorption peak is as a result of transitions to excited states close to the conduction band determined by the trapped electron is justified. Energy level diagram for an F center as shown in figure 19.3 clearly shows that F absorption band is created due to a transition from the ground state to the first excited state below the conduction band. Coloring of crystals by addition. It has already been explained that the intrinsic concentration of defects in the alkali halide crystals can be upset by getting them in contact with alkali metal. This effect can also be produced in the crystals by getting them in contact with halogen. The latter will be discussed further. In several materials, significant effects on ionic and electronic conductivity and optical properties can be produced in this way. Taking the example of KCl, that's potassium chloride, it can be additively colored by sealing in an evacuated glass tube with potassium metal and then heating in a furnace. Figure 19.4 shows the experimental setup for additively coloring of KCl crystal. It consists of a double furnace and an evacuated glass tube. KCl crystal and potassium metal are placed in a sealed evacuated glass tube. The temperature T1 is around 500 degrees centigrade, whereas temperature T2 is maintained at some appropriate value as may be required for the desired concentration of defects. In this way, an alkali halide crystal such as KCl is heated in an atmosphere of potassium vapor. The temperatures T1 and T2 are maintained for a few hours and then the tube is removed. The crystal is then quenched in an oil bath or preferably on a copper block. It results into coloring of the crystal due to creation of F centers associated with non-stoichiometry. The density of F centers depends upon the density of potassium ions in the vapor and therefore the temperature T2. In fact, it is the temperature T2 which controls the vapor pressure of potassium and hence the concentration of color centers. Figure 19.4 is a schematic diagram of the experimental arrangement for additively coloring KCl crystal. In figure 19.5 is shown a plot of concentration of F centers drawn against the density of alkali, that is potassium, metal atoms in the vapor as determined by the temperature of the potassium metal shown as T subscript 2. The plot is drawn for two temperatures, namely T subscript 1, at which the alkali halide, that is the KCl crystal, is maintained. Figure 19.6 shows the F band produced as a result of heating an alkali halide, that is KBr crystal, in potassium vapor and then quenching in the dark from high temperature. If we take pure KBr crystal, it is found to be almost transparent from 0.025 electron volt, which falls in a rest tolerant region, to above 6.5 electron volt, which falls in the ultraviolet region. The same is not true for the additively colored crystal. The said colored crystal shows an F band at 2.1 electron volt, which is essentially due to excitation of the electron from an approximate 1s ground state to a 2p excited state. Excitation to 3p, 4p and higher lying p states results into K band. Figure 19.6 shows a spectrum with the F band and other absorption peaks in an additively colored KBr crystal recorded at 10 degree Kelvin. An additively colored crystal at room temperature, when exposed to F band light, some new bands are observed which lie on the long wavelength side of the F band. Such wavelength bands are a consequence of aggregates of the F band and can also be produced by holding the colored crystal at an elevated temperature of say 100 degrees centigrade for a few hours, or also by exposing the crystal to X-rays. Most prominent of these long wavelength bands are known as capital M bands. Still higher aggregates of the F center are called as capital R and capital N centers. Figure 19.7 is an example of M, N, R1 and R2 bands when KCl is irradiated in F band at room temperature. The curves marked second and third are the curves obtained as a result of successive stages of irradiation. The curve marked 1 shows optical density after heating the crystal to 500 degrees centigrade and then quenching it to room temperature. M, N and R bands are not formed if the crystal is quenched and then illuminated at low temperature. It means that the additively colored crystals are stable against the creation of aggregate centers at temperatures of below 200 degree Kelvin. Figure 19.7 shows M, N, R1 and R2 bands as shown by KCl on irradiation in the F band at room temperature. Second and third curves taken after following successive stages of irradiation. Number 1 curve taken after heating the crystal to 500 degrees centigrade and then quenching to room temperature. A broad new band known as F prime band is observed when an additively colored crystal of KBr is illuminated with F light. at around 123 degree Kelvin, as is shown in figure 19.8. Let us know what these different absorption bands observed in alkali halide crystals are. It is summarized as follows. Number 1. An F center is an electron trapped at a negative ion vacancy. Number 2. L1, L2, L3 are very weak absorption bands and are thought to be higher excited states of the F center. Beta band is closely related to F centers. Its formation is attributed to excitons produced by absorption of a photon near about the F center. M center is a pair of neighboring negative ion vacancies in addition to two electrons. So it is a combination of two F centers. Fourth, R center is due to three halogen ion vacancies in addition to three electrons. R and N centers are higher aggregates of the F center. Number 5. F band is due to single negative ion vacancy in which two electrons are trapped. Number 6. Alpha band is due to exciton absorption in the immediate vicinity of the isolated vacancies. Number 7. Heating an additively colored crystal in hydrogen gas or by growing a crystal with an addition of an alkali hydride results into substitution of negative hydrogen ions, that is H negative ions, in place of halogen ions. A new absorption band known as U band in the ultraviolet region at 5.5 electron volt is shown by KBr. The energy level scheme for a KCl crystal is shown figure 19.9. The V centers. If an alkali halide crystal is heated in halogen vapor, a stoichiometric excess of halogen ions is produced in it. We have already known that heating an alkali halide crystal in metal vapor results into a series of color centers. In the same way, we expect a new series of color centers as a result of heating the crystal in a halogen vapor. These new centers, known as V centers, have holes in place of electrons. V bands can also be produced by exposing alkali halide crystals to intense penetrating X-rays. The absorption bands produced in KBr crystals at 80 degree K after irradiating them to intense penetrating X-rays are shown in figure 19.10. The familiar F, F prime and alpha bands are seen, but in addition, there are other centers giving rise to V1, V2 and V3 bands which occur in the ultraviolet region. Color center models. The models of various color centers as described in the previous section are shown here through schematic representation in figure 19.11. F center is an electron trapped at a negative ion vacancy. F prime center is F center combined with one electron. R1 center is F center combined with a vacant anion site or one electron bound to two anion vacancies. R2 center are two F centers combined or two electrons associated with two anion vacancies. M center is F center combined with a pair of vacancies, opposite sign, or an electron bound to two anion and one cation vacancies. Model of V centers. The models of various other color centers, as described in the previous section, are shown here through schematic representation in figure 19.12. V1 center is an antimorph of the F center. It is hole trapped at a positive ion vacancy. V2 and V3 centers are antimorphs of R center. V2 is due to two holes trapped by two positive ion vacancies, and V3 is due to one hole trapped at a pair of positive ion vacancies. M4 center is an antimorph of M center. Now let us talk about polymorphism. You see, in several cases, it so happens that the same chemical compound manifests itself in two or more than two different structures and which exhibit divergently different properties and characteristics. It only establishes the fact that physical properties of a crystal do not depend only upon the atoms or molecules which constitutes it, but on how they are arranged in the crystal structure. Crystals manifest structure-sensitive properties, be it mechanical, optical, electronic, or any other. Polymorphism is a term used for a phenomenon in which a chemical compound crystallizes in more than one form genetically distinct. A chemical compound may crystallize in two different forms. It is then said to be dimorphous, and if in three, it is called as trimorphous, and so on. In general, it is said to be polymorphous, and the phenomenon is called polymorphism. There are several examples of such compounds which exhibit dimorphous. Carbon atoms arranged in one particular type of structure makes a diamond, whereas when they are arranged in a different structure, it becomes graphite. The two are different structures which display different properties, though both have carbon as constituent atoms. Similarly, calcium carbonate, that is CaCO3, manifests itself in two forms, such as calcite and as aragonite. Calcite falls under the rhombohedral class of the hexagonal system, whereas aragonite appears as orthorhombic crystals. The optical characteristics of calcite and aragonite are entirely different. The specific gravity of calcite is 2.7, which is lower as compared to that of aragonite. The specific gravity of aragonite being 2.9. The divergently different optical and mechanical properties of diamond and graphite are well known. Titanium dioxide with a chemical formula TiO2 is trimorphous. It appears as a tetragonal structure with C equal to 0.6442 and known as rutile. Its second form is tetragonal with C equal to 1.778, which is known as octahydride. The third form is orthorhombic and it is known as brookite. The manifestation of titanium dioxide in these three different structures is reflected by their different properties as well. So, the students, let us summarize what we have learned in this module. The discussion has led us to learn about particular type of defect known as color centers and how to achieve their creation. We have also learned about the procedure for creation of color centers by addition. We have also learned about various types of color centers as has been already described and the models which have been suggested for these centers. The explanation of these models has already been given. Phenomena of polymorphism is also described. Thank you.